Right, so let's take a look at the June 2012 Applied Physics paper. So let's start off with question 1. So we've got a child's pop gun, and the piston is pushed quickly along the barrel, compressing air. When the pressure is high enough, the cork is expelled at high speed from the end of the barrel. Figure 1 shows the gun before it's fired. The air in the barrel is at a pressure of 1 bar, or 1 times 10 to the 5, and a temperature of 290 K, and the volume is 2.1 times 10 to the minus 5 meters cubed. The volume of air in the barrel at the instant the cork is expelled is 1.2 times 10 to the minus 5. Calculate the pressure, assuming it's compressed adiabatically. So adiabatic means that PV to the gamma is a constant. So in this case, what we want to do is find P2. So we know that P1 V1 to the gamma is equal to P2 V2 to the gamma. So we can write that as P2 is equal to P1 V1 over V2 to the power of gamma. So we can put values in. So we've got P1, and you've got the initial volume is 2.1, the final volume is 1.2. We can get rid of the 10 to the minus 5 because it's a ratio, and that's the power of 1.4. So let's grab the old calculator. 2.1 divided by 1.2, the power of 1.4 times 1 times 10 to the power of 5. And that comes out as 2.18 times 10 to the 5. So it's going to be 2.2 times 10 to the 5 to 2 significant figures there. Okay, so calculate the maximum temperature reached by the air in your gun, giving your answer to the correct number of significant figures. So in all processes where we have a constant mass, we have this expression which is derived from the ideal gas equation, and we want to calculate T2. So that's going to be P2 V2 T1, and all divided by P1 V1. So that's going to give us, so we've got 2.2 over 1.0, actually it's 2.18. The 10 to the 5 is going to cancel, and then we have the volumes, and that's going to be 2.1, and then we're finally by the temperature. So all of the powers of 10 have ended up cancelling when you have the fraction, so you have 2.2 times by 1.2 divided by 2.1 times by 290, and you end up with 364.57, yada yada yada. So 2 sig figs is appropriate here, so it's going to be 3.6 times 10 to the 2 Kelvin, so giving it 2 significant figures there. The work done needed to compress the air adiabatically from 1.1 times 10 to the minus 5 to 1.2 times 10 to the minus 5 is 1.4 joules. Use the first law of thermodynamics to determine the change in internal energy during compression, explaining how you arrived at it. So the first key thing is that it's adiabatic, which means that the heat exchange with the surroundings is 0. So what we have is Q is equal to W plus delta U. So what we have is that the delta U is going to be equal to minus W. So essentially what you get is a change of minus 1.4 joules, and it's all to do with the fact it's adiabatic and that Q is 0. So if you're putting work in, you're going to essentially increase the internal energy, or if you're taking work out, you're going to decrease the internal energy. Okay. Explain, giving your reasons, whether the volume of air in the barrel at the point when the cork leaves the gun will be less than, equal to, or greater than the 1.2 times 10 to the minus 5 if the handle gun had pushed in slowly. So slowly is going to be an isothermal type process. So the way to think about this is the cork is going to be pushed out when it reaches a certain pressure, because it's going to take a certain force to overcome friction to push the cork out. So during a adiabatic process, what you get is it looking like that. But then when you switch to an isothermal process, you get a line which is a shallower gradient. So if you look at this, what you're going to end up with is you're going to need a larger change in volume, if we map those out, than we did with the adiabatic one. So let's put that in. So we're going to need a larger change in volume to reach the same pressure, and then the piston needs to be pushed in further. And that's all to do with the contrast between adiabatic and isothermal. So the adiabatic is this steeper line, so you get a greater increase in pressure for the same change in volume. So to reach the same pressure, which is what you'd need for the cork to pop out, you need a larger change in volume. Alright, so for question 2, we've got a circular saw, and it's rotating at 2600 revolutions per minute, and against a frictional torque of 1.2 Newton meters acting from the bearings. The horizontal force of 32 newtons is needed to push the piece of wood into the saw. The force acts on the blade at an effective radius of 0.15 meters. Calculate torque on the saw blade resulting from the horizontal force. So torque is the force times the perpendicular distance. So that's going to be 32 times by 0.15, which gives you an answer of 4.8 Newton meters, because it's a torque. Calculate the output power of the motor when it is cutting the wood. So the first thing, we're effectively going to need to do this. So first we need to get the angular speed. So the total torque is going to be the two torques added together, because you're going to need to both overcome the frictional torque and provide this torque to actually push it on. And we need to turn revolutions per minute into radians per second. So multiplying by 2 pi turns into radians, divided by 60 turns it into per second. So let's grab the old calculator. 4.8 plus 1.2 is 6 times 2600 times 2 times pi divided by 60, and that comes out as 520 pi, or it's 1.6 times 10 to the 3 watts. So the key here is to recognise you need both the resultant torque and the frictional torque to give you the total torque. It's the total torque that goes in here, and you need the angular speed in radians per second. Okay, so immediately after cutting the wood, the motor is switched off. The time taken for the blade to come to rest is 8.5 seconds. Calculate the moment of inertia of the rotating parts, stating an appropriate unit. Okay, so we know the initial angular speed is 2600 times 2 pi over 60. We know the final angular speed is 0. And we know the time is 8.5, so from that we can calculate what the angular acceleration is. It's going to be Wf minus Wi over 8.5. So let's calculate what that is. What's my calculator? So 0 minus 2600 times 2 times pi divided by 60 divided by 8.5 gives you minus 32.0319. And then you know inertia is the torque divided by the angular acceleration. So the torque was from the friction, so it's going to be the 1.2 divided by the but it's going to be acting against the motion, so it would be minus, so the minus signs cancel, yada yada. So let's do 1.2 divided by the answer, gives you 3.7 times 10 to the minus 2. We're expressing it in standard form. And the unit of moment of inertia is kilogram meter squared. That's the standard unit of torque you get given. Alright, so that's that one complete. The blade is accidentally touched when it's rotating. An electronic safety brake stops the blade in 5 milliseconds, fast enough to prevent serious injury. The safety brake works by forcing a block of aluminium into the saw teeth. Estimate the rate at which the rotational kinetic energy is dissipated as heat in deforming the aluminium when it operates. So we need to work out the change in energy, which is going to be it's not m, what am I doing? It's the moment of inertia because we're looking at rotational kinetic energy. So let's substitute the numbers in there. So I've still got the inertia in my calculator, so I'll divide that by 2 and times by 2600 times 2 times pi divided by 60 all squared gives you, I'm going to keep this in its rounded form, 442 pi. And that happened over 5 milliseconds, so divide by 5 times 10 to the minus 3. So it's change in energy divided by 5 times 10 to the minus 3. And when we plug that in, we end up with a value of 27716, or 2.8 times 10 to the 1, 2, 3, 4, 5, 10 to the 5 when we express it in standard form with the correct number of significant figures, or I suppose you could write it as 2.8 times 10 to the 2 kilowatts if you wished. Okay, so now we're looking at a steam engine, and it's used to demonstrate energy transfers. The steam engine drives a dynamo which requires a constant torque, so we want to output a fixed torque. By the means of valves, high pressure steam is applied to one side of the piston on the outward stroke as shown, and to the other side of the piston on the inward stroke. Oh, I see, so we can keep it going in the same direction, presumably. Yep. The motion of the piston is converted into rotary motion by the connecting rod and crank. A flywheel is also fitted to the crankshaft. Figure 4 shows that the torque on the crankshaft due to the engine varies with angle, and also shows what we're looking for in terms of the steady dynamo torque. State and explain how you could use figure 4 to determine the work done by the engine in 1 revolution of the crankshaft. So work done is torque times the angular displacement, so that's going to be the area under the graph, and it's asked for in 1 full revolution, so 1 full revolution is going through from 0 to 2 pi. So it's gone through, well, it looks like 2 cycles there, but it's gone to 1 full revolution by 2 pi. And the reason for that is this equation here, so how you get work, and that's by multiplying the values on the axes. The dynamo has low moment of inertia. Explain why the engine torque varies over a cycle. Explain why, in terms of kinetic energy, it is necessary to fit a flywheel, and discuss the motion, how the motion of the crankshaft is influenced by the value of the moment of inertia of the flywheel. So let's take these points one by one. So why does engine torque vary? So looking why the engine torque varies over the cycle. So the pressure on the piston is going to vary during the cycle, because obviously it's expanding and compressing, so the volume is changing, and so you're going to get a change in pressure. But the area is fixed, so then force varies, and if force varies, then your torque varies too. So essentially, those are the stages which lead to you getting varying torque, because you're going to have it changing during the cycle. So that's why the engine torque varies over a cycle. Explain why it is necessary to fit a flywheel to the crankshaft of the engine. So we want to output a fixed torque. So the flywheel is essentially there as a means of energy storage, and it allows you to supply the extra torque when you need it, when your engine's not producing enough, or it allows you to spend any excess torque accelerating the flywheel. So your flywheel stores kinetic energy, and it's a rotational type of kinetic energy. So when engine torque is less than dynamo torque, it provides power, so it essentially makes up for it. And also when the engine torque is greater than the dynamo torque, it stores energy, so it takes some of that torque and uses it to accelerate the flywheel. So that's essentially the function of the flywheel. So it allows you to get a uniform torque out. So discuss how the motion of the crankshaft is influenced by the value of the moment inertia of the flywheel. So the problem with having varying torque is that will cause the angular speed to vary, because your angular acceleration is going to vary. So if you have a high moment of inertia, what that does is it smooths that out, so you get smaller variations in speed, because it's difficult for the torque to change the speed of the overall system, so you get a nice, smooth, uniform speed. So that's the function of it, and is why you'd want a high moment of inertia. Gives you smaller fluctuations in engine speed. So if you want to apply uniform torque, you want a fairly uniform engine speed, and you can do that by having the high moment of inertia. Because if you think about it, the torque and the acceleration are linked by the moment of inertia. So if you have a high this for a certain torque, that reduces the angular acceleration there. So that's what you would be looking for in answering that question, and we've now essentially addressed those 3 points. Okay, so we've got a 4-stroke diesel engine with 4 cylinders. It's running at constant speed on a test bed. An indicator for 1 cylinder is shown in figure 5, and other test data are given below. Alright, so I'm guessing we're going to end up calculating an area under this. Looks suspiciously like it. Oh, and what do you know, it's asking you in the next question to calculate indicated power. So just to show you how I normally approach this, I'm looking for complete squares. So we've got 1, 2, 3, 4, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, probably about 20 squares there overall on this one here. So there's 20 squares. Each square represents 0.5 times 10 to the 6 times by 0.05 times 10 to the minus 3, which let me grab my calculator. So 0.5 times 10 to the 6, 0.05 times 10 to the minus 3. Each square represents 25 joules overall. If we have 20 squares and each one of those is 20 joules, so 20 times 25 gives you about 500 joules per cycle. So for your next part, so the area is approximately 500 joules. So indicated power is area times by cylinders times by cycles per second. So it's 500, and that's multiplied by the number of cylinders, which is 4, times by it's going to be what, 4100 RPM divided by 60 gives you the number of revolutions per second, but it's 4 strokes, so you multiply by 0.5 because every other stroke is a wasted stroke effectively. So let's type those in: 4100 divided by 60 times 0.5 times 4 times 500, and you come up with a value of 68,330, so it's going to be 6.8 times 10 to the 4, we don't want it in kilowatts, so it's just going to be 68, giving it in kilowatts. Calculate the overall efficiency of the engine, so we need to get your power input, which is going to be the calorific value, so 38.6 times 10 to the 6, and then you're going to times that by 0.00376, that's in litres per second, which gives you 145 kilowatts. Power out is 55 kilowatts, so the efficiency is 55 divided by 145, so 38.6 times 10 to the 6 times 0.00376. That's your total in. 55,000 divided by answer gives you a 0.38 or 38% efficiency. There. So for the overall efficiency, is the total power out divided by total power in. Account for the difference between indicated power and brake power. So it's going to be, you subtract from it the frictional power, so it's going to be work done against frictional torques at the bearings. So frictional torques tend to act at the bearings on which it's mounted, so it's going to be doing that. You could also probably have said that you're taking energy to pump things like coolant and oil around your engine, or to do work during the exhaust phase, any of those kind of things. What is represented by the line AB on the figure. So that's your exhaust. First of all, your exhaust and induction phases. So that's the second. So it goes through 2 full cycles per working cycle for a 4-stroke. So and the second cycle is exhausting and induction, and those take place at around atmospheric pressure typically.